Well, hey guys, if we're doing this right, we're recording, and this should be our Honors Chapter 8, Part 2. So, just to do a quick review, last class we were talking about angular quantities. We're talking about rotational motion. So, just to reiterate a few things from last time, we learned our angular displacement, which we said we'd measure in radians, which was our rotational counterpart to our regular displacement. Our regular displacement, of course, we measured in meters. So last time we learned this whole idea that there are rotational versions of all of our translational quantities. So angular displacement just means we're measuring a displacement in terms of an angle instead of a distance. So in other words, if we think about somebody moving in a circle from point A to point B, they travel that length in meters. And another way of looking at it is they travel that length, that angle in radians. So the same exact journey can be described equally well in meters, but that same journey could be described in terms of radians via this angle. And from that we built up that we had angular velocity, which was just displacement over time, exactly like we'd expect from regular velocity, displacement over time. We learned that you can accelerate in a rotational way. That would just be your change in velocity over time. And our regular acceleration, to reiterate, would be our change in velocity over time. Change in regular velocity over time. So that gives us all of our angular quantities and how they relate to our regular linear quantities. When we learned all of our kinematic variables the first time, the next thing we did was we then started exploring, well, how do you actually get things to accelerate? Newton's first law says things don't want to. And we came up with Newton's second law, that force equals mass times acceleration. Well, where we're headed is ultimately to come up with the rotational or the angular version of this equation. We're not actually going to come up with this equation in the rotational sense. We're not going to come up with that today. But what we are going to start doing is talking about angular force. If a regular force causes a regular acceleration, then an angular force will cause an angular acceleration. And what I want to do today is talk about that angular force. We're going to use the symbol tau. That's the Greek letter tau. It's basically a T with a curly on top. Tau is going to be our symbol for torque. Actually, I guess I shouldn't have written torque with a tau. Tau is going to be our symbol for torque, and that's going to be tau. Now, tau is going to be our angular force, and eventually we're going to relate this to angular acceleration. So torque will eventually be related to our angular acceleration. Again, we're not setting that up today, so today we're just going to say it's proportional to, or we're going to say that torque causes an angular acceleration. So let me just iterate that here. I'll draw a picture. I'll see if I can demonstrate that. So imagine if we had, let's see how we can describe this. So imagine that we have a meter stick on a table and we've got the meter stick attached to a hinge. So right here's a little hinge, there's a meter stick, and here's my table. So there's my table legs. And if I were to apply a force to the meter stick right there, so if I were to apply a force on it right there, this meter stick would rotate. It would rotate to some other position. It would move that way. And in doing so, we can look at it like this. The meter stick, before I push on it, has zero velocity. When I start pushing on it such that it causes a rotation, so now it's rotating, now it's rotating, so it had no velocity. As I'm pushing on it, it ends up having an angular velocity. It is displacing that angle in some time, so it has no velocity. I start pushing, it rotates around, now it has angular velocity. And the fact that it went from zero to some angular velocity means necessarily that it accelerated in an angular sense. So if I push on this, causing it to rotate, it will experience a rotational angular acceleration. Again, we'll go into the actual equation that we'll come up with for this another day, but today we're going to talk about just torque itself. I just wanted to plant the seed that where we're headed is that we can cause accelerations. Excuse me, I got a little bit of hiccupy there. So anyways, torque will ultimately, we'll see, cause an angular acceleration, but today I just want to explore torque in general. And this little demo here I think gave you a good idea of what torque is. It is a force that causes a rotation. So let's look at our equation for torque. And again, remember, we're not trying to set it up equating to angular acceleration today. So our equation for torque is going to equal, and I'll write the equation out and then we'll explain all the pieces of it. So there's our equation for torque. It equals Rf sine theta. So what is this going to look like? Well, it's going to depend on the force. So if I apply a force to my little meter stick and cause it to rotate, then the amount of force I apply is going to have an impact on the amount of torque. If I apply a small force, I will end up with a small little acceleration. In other words, I end up with a small torque. If I apply a huge force, this is going to go flying that way. It'll have a huge acceleration and therefore a huge torque. So small force makes small torque. Large force will make large torque. So the amount of force affects the amount of torque. Now, it turns out that this sine theta term is very important, and I will draw another picture right here to demonstrate that. There's my pivot point, there's my meter stick. Instead of applying a force like I did here, perpendicular, I'm going to apply a force this way. So let's apply a force in the same direction. So instead of applying perpendicular, I'm going to apply a force parallel to the meter stick. I hope you agree that if I apply a force vertically on this meter stick is not going to rotate. We are not going to start it rotating if I push that way. It's going to do something, but it won't rotate. It'll just move it that way, or the hinge is so strong that it can't move at all. So that does nothing for rotational motion. That causes rotational motion. So perpendicular seems to be good. Parallel seems to be bad. If I apply a force at an angle, now I'm applying a little bit in this direction, so we have our x component, but we also would have our y component. Well, the y component is not going to cause any rotation. The x component will actually work just like this did and cause rotation. So the direction of that force matters. And as it turns out, the part we care about is the part of the force that's perpendicular. To get the perpendicular component of that force, if there's my angle, no, I guess I'm saying this wrong. I drew this backwards. I'll draw you a better picture in a second. Hold on, now I'm all messing up my thing. I'm just going to draw a whole better picture. Anyways, the sine theta is the way we get the perpendicular component. Remember back to our vector analysis, if we had some angle, some vector A, sine, if we wanted to know the perpendicular component, the component going in the y direction, that would be sine because it's opposite. Opposite means sine. So this gives me the perpendicular component, the component that's perpendicular to the radius there. Okay? So we now know that the force matters, the direction of the force matters, and then we have R. As it turns out, if I apply a force, if I apply a force way up here, then I get a lot of acceleration. If I apply a force way down here, I will not get much acceleration. Another way to think about this, if you've ever held a door open for somebody, you've noticed if that's the hinge, this is the top view of a door, that's the hinge. If you push the door way out here, it's easy to hold it open. If you try to hold the door here, you'll notice it's very difficult. Where you apply the force matters. That's what R is. So this equation, a way we can visualize it, there's some object, it has that length. I'm going to apply a force on that object right there, and I'm going to apply a force in that direction. So F is the force I'm applying. Sine theta comes from the direction of my force. R is not the length of the object. That is not the length of the object. R is the length of the location of the force. So if we consider this the pivot point, so I apply that force, this is going to slowly rotate that way. As I apply the force, the vertical component will cause rotation this way around that axis. R is the length from the pivot point to the location of the force. So R is not the length of the object, R is the length from the pivot point to where the force happens. That gives me R. Then we get torque. And of course, just so I can reiterate that, that would be our F sine theta, would be that component. Okay? So, torque. It is an angular force. It causes an angular acceleration. We'll see how to connect it to acceleration later. Right now, torque, the angular force, is going to be related to where I apply a force, the direction I apply that force, and the amount of force I apply. I'm hoping that that actually makes a little bit of sense here. The units for torque. Well, force is in newtons and R is in meters, so our units would be the Newton meter. As far as I can see, that's basically everything I want to say about torque. The next thing I want to do is actually go do some problems. So let's stop the video and I'll do a couple of problems live up at the whiteboard. So